Thanks, Dr. Chen, for his presentation. And the second part is the reasoning for graph-based recommendation. Here's the structure of the presentation, including introduction, preliminary, literature review, and the conclusion. The recommendation task can be used in many scenarios in the real world. For example, in the e-commerce recommendation, we have Amazon and Taobao in China and etc. They always recommend products according to our purchase history and other information. And also in the recent micro video application, like TikTok, it also usually recommend micro videos that what we liked similar or by whom we liked. Moreover, in the post recommendation, like Twitter, it always recommend our interesting tweets. And in point of interest recommendation, like Yelp, it recommends where we would like to go next. And the recommender systems could save customers time to recommend their interesting products. And for the merchant, the recommender system could learn each customer's interest and recommend proper advertisements to them to bring profits to the merchant. And because the application seems to know the customer's interest, so it also could catch customers' attention and makes the customers more tend to spend time on the application. And currently, the recommender systems can already obtain high performance thanks to the development of graph neural networks. As mentioned in the first part of the tutorial, and more researchers bring the attention to the explainable of the models. And why are the explainable recommendations important these years? And the first reason is to avoid black box. Due to the high performance of neural networks, many recommendations use them to learn users' interest to improve the effectiveness of recommendation. However, the shortcoming of the neural network also brings to recommender systems, including the black box nature. The second reason is that giving reasons for recommendation could facilitate system designers to diagnose, debug, and refine the recommendation algorithm. Last, providing explanation can also give more persuasive, transparent, trustworthy recommendations. People are more likely to choose recommendations with explanations instead of those without explanations, because it seems the recommendation more persuasive, and explanations will increase the user stickiness for the application. Next is the preliminary. So what is explainable recommender system? And here is a definition. They not only provide users or system designers with recommendation results, but also explanations to clarify why such items are recommended. And the inputs of the explainable recommendation are each user's historical items. Sometimes each items attributes, and sometimes each user's attributes, like the social information. And the output are the predicted items for each user and the explanation for each recommendation. So the evaluation always includes two parts, the performance of the recommendation results and the quality of the explanation. For the evaluation of the performance of the recommendation results, there are many metrics to evaluate. And I will introduce 4 frequent evaluations. Hit ratio at K is always used to measure the ratio of the recommendation system hit to the correct items, and which reflects the recall quality. Here's the equation. The molecular is the number of the correct predicted item in the top K candidate items, and the denominator is the number of candidate items. Another evaluation of the performance of recommendation is NDCG, which calculates the cumulative results with normalization. And here's the equation. It is also a kind of recall evaluation, but it also related to the rank of the correct item in the candidate's prediction list. The higher the correct hitting rank, the higher is the score. And precision at K is the ratio of predicted correctly in the top K prediction sets. And the molecular is the number of hit items in the top K prediction list, and the denominator and the denominator is the number of the prediction set. And the recall at K is the ratio of predicted correctly in the top K test sets. And the molecular is the number of hit items in the top K prediction list, just the molecular in the prediction at K. And the denominator is not same. It's the number of the correct items. And for the evaluation of the explanation, there are currently 4 types. The first is user study, which will design some questions or tasks for the subjects to answer or complete. And conclusions will be derived from the responses of the subjects. This kind of evaluation will spend much human efforts, so it is not usually used in recent years. And another kind of evaluation is called online evaluation, which says if the explanations can help to make users accept the recommendations. It usually tests online. For example, on a commercial web browser, the experimental group receives testing explanations. The comparison group receives the baseline. People also view the explanations, and a control group that receives no explanation. The click-through rate of each group is calculated to evaluate the effect of providing personalized explanations. This kind of evaluation also need human involved. and need even more human efforts because it should make the recommendation online and then collect and do data statistic. Another is called offline evaluation. Actually, this kind of evaluation are all equation based. One of them is model fidelity, which evaluates the ratio of explainable recommended items in all recommended items. So the molecular is the explainable items in all recommended items, and the denominator is the recommended items. The higher the score is, the better explainability is. Another kind of offline evaluation is blue. Actually, it is an evaluation for the quality of sentences, which shows how the generated sentences similar to the human generated ones. Therefore, if the recommendation use sentences as explanations, blue can be used to evaluate the quality of sentence. And this is the blue equation. Actually, this PN equation is the core of blue evaluation, which means the precision of the generated n-gram compared to the ground truth n-gram. So blue score reflects the precision of the generated sentence. Another is called rouge, which is also an evaluation to reflect the quality of sentence. But rouge shows the recall of the generated n-gram compared to the ground truth n-gram. Here I only gave two examples, blue and rouge, to evaluate the sentence. In fact, if the explainable recommendation use sentences to explain the recommendation, the sentence evaluations can be used to evaluate the quality of explanation. And here is another kind of evaluation, is a case study, which can help to understand the intuition behind the explainable recommendation model and the effectiveness of explanations. This kind of evaluation are always used in recent years. For example, in this figure, user 273 has bought a microphone pop filter and then right angle instrument cable. In the below, there are three paths from the pop filter to the cable. And these three paths are the explanations to buy right angle instrument cable. So case study is to randomly select user and show how the recommender system provides explanations. Next is the literature review of the graph-based explainable recommendation. I classify the graph-based explainable recommendation by the type of graph and then the type of explanation. On the homogeneous graph, the recommendations always use collaborative information as reasoning. This kind of method always constructs a bipartite graph from the recommendation data, which only include users and items. So they usually use collaborative information to explain the recommendation. No matter how they provide the explanation, including use user or item to explain, use the textual sentence to explain, and so on. The core of the explanation are all based on collaborative information. For example, here's a work use collaborative information and a sentence template to provide explanation. The explanation is the item is recommended to client 4 because it's similar to client 5 and client 6 in the first cluster who also bought this item. However, this kind of explanation only involves collaborative information and ignores some external information, unlike the attributes of the items. Therefore, the explanation tends to be improper and one-sided. So there's another graph type, which is heterogeneous graph. In this kind of explainable recommendation, it considers users, items, and also other external information to enrich the training data and learn many sites to provide explanations. So the explanation tends to be more kind of other than the collaborative information. One of the type of explanation is to use words, words to explain. Here's an example to use the attributes of music as the explanation, including singer, album, and so on. And in the figure, the left squares are the attentions of each attribute. We can see that the second line squares are singer attentions, and the third line squares denotes the album attentions. The darker the square is, the more weight of the attention. So the reason for user listening to this second music is more because of the same album as the first music. And another type of explanation is to use sentence. Here's an example to use sentence to explain the recommendation. This work constructs a knowledge graph with entities, including users, items, and items attributes. It uses a naive breadth first search, which is BFS, to explore the shortest path, and then generates the textual sentences according to templates. In this box, it is the explanation. B9C is recommended because the user often purchases items that are bought with BTU together, and B9C is also frequently bought with BTU together. However, this kind of explanation is sometimes not fluent because of the bottleneck of the natural language processing method, and use the template to express sentence is always too boring and stock. So in recent years, researchers tend to directly use path to explain the recommendations on the graph. Because intuitively, a path with length 2 on the graph represents the relation between two nodes, and path with more than length 2 represents compositional relations. And there are two kinds of paths to explain the recommendation, meta path and meta path instance. The first one is a kind of path schema, and the second is a specific path. A meta path is an ordered sequence of node types and edge types defined on the network schema, which describes a composite relation between the nodes types involved. And for example, the meta path author could indicate the co-author's relation between the two authors. And the author paper, venue paper author, could represent two authors who published papers in the same venue. So the metapath is meaningful, and it could explain some relations among the nodes. Here is a typical path-based explainable recommendation. And we can see that each meta path represents a semantic meaning in the model. And this semantic meaning can be served as the explanation of the recommendation. For example, the meta path UU means the friends of the target user. So if giving recommendation through this meta path, the explanation is his friend also bought this recommended item. But the shortcoming of this kind of method is that the meta path is a kind of high-level path. Meta path presents a set of paths, and it is a kind of schema. Therefore, this kind of explanation is too general and high level. And after that, a meta path instance concept is proposed and later used to improve recommendation. A metapath instance context is the general information of several instances from the same start node to the same end node. And taking this Alice and her music as an example, here I list all metapath instances from Alice to IC The first path is Alice to Shape of You to Ed Sheeran to IC The second is Alice to Shape of You to Tony to IC And metapath instance context from Alice to IC is the first instance and the second instance with some weights. So this is the metapath instance context concept. And here's a work used the metapath instance to explain the recommendation. In the figure, it generates the metapath instances according to the predefined metapath schemas and learn the attention weights of the instance passes through a self-attention module. Finally, it uses the paths with weights as the explanations. Here is the case study for the explanation. As I mentioned before, it randomly selects a user and directly display the paths it generated to show the explainability. This kind of explanations are used frequently in recent years. However, the evaluation is to use case study to show the explainability, not metric-based evaluation. It is one of the shortcomings of this kind of explanation. Moreover, another type of explanation is to use a visual graph. Here is a related work use visual graph to explain the recommendation. The predictions are based on a collaborative analysis of preference data from a user's direct peer group on a social network. Users also learn a wealth of information about the preferences of their peers through interaction with the visualization. Such information is not easily discoverable in traditional text-based interfaces. This figure is the interface of the recommendation application. They construct a social graph using users' items and user social information. And for user X in the layer 1, he has bought the item I to A, and his friend in the layer 3, U 3A, also has bought the same item, and he has also bought item I 4A. So the recommender system recommends I 4A to the user X. The showed visual graph can be regarded as the reasoning. And finally, is the conclusion. We introduced the recommendation system and its explainability. And we classify the explainable recommendation into the following types. In the homogeneous graph, they usually use collaborative information as reasoning. And in heterogeneous graph, they usually use words, sentences, path, visual graph as reasoning. And roughly, the explainability and the performance of the recommendation are of this relation. When the performance is low, the explainability is good, and otherwise, the explainability is low. That is because the deep learning based explainability always could get better performance, but the black box nature also makes the recommendation less explainability. However, methods without the deep learning methods always could get better explainability, but their performance cannot outperform the deep learning recommendations. The goal of the explainable recommendation is to keep high performance of the recommendation and also provide better explainability. Here I list several future directions of the graph-based explainable recommendation. The first one is dynamic graph explainable recommendation. Sequential feature is an important information in recommendation and explanation. For example, in this figure, it is unlikely for the user to firstly buy a guitar string and then buy a guitar. This sequential information is not only necessary for the recommender system, but also important information when giving explanations. Because this temporal information can also be an explanation to buy a guitar string. However, the existing graph-based explainable recommendation are most based on a static graph. In this way, it is hard to model the dynamic evolution of the recommendation graph. The challenge is how to design an effective and efficient dynamic graph model to do explainable recommendation. And besides, the causality-based graph explainable recommendation is also a future direction. Actually, the causal learning has been adopted in machine learning to provide causal relation for better explainability in model. But it has not been used in the graph-based explainable recommendation. The challenge is how to combine the causal learning in graph to do recommendation and provide the explanation. Another is the sentence-based graph explainable recommendation, which is use a high-quality fluent sentence sentences to provide the explanation in the graph-based explainable recommendation. Actually, it is always a hot topic. However, the bottleneck is the natural language processing technology. In addition, the evaluation for quality of explainability is also an issue. Currently, most of the papers use case study or user study to test the quality of explainability, which is insufficient. It is better to use a metric-based method to evaluate and alleviate human involving. But the challenge is how to define the good quality of the explanation and how to use metric to evaluate. It is hard to use metric to calculate the quality of the explanation. And that's all. Thank you.